Hello, AP Chemistry, and welcome to the last of Chapter 16. So, structure, as it affects acidity. Okay? That's an I too. All right, and this is actually a D. As it affects acidity, right? So, let's just think about what that means, right? Because we need to have a really strong definition of what that means before we start analyzing structures to decide if it's more acidic or not, right? So, if we're going to say that we increase the acidity of something, right? What that's basically saying, right, is that it is easier, more able, or more readily, let's say that, more readily loses the proton, where the proton is our H, yes? So, if we increase the acidity of something, what that really means is that it more readily loses that acidic proton. Let's say that, acidic proton, that's nice. Okay, so it more readily loses the acidic proton, right? And that's going to boil down to three basic considerations, right? One, bond polarity, right, of the acidic proton, right? The bond strength, right, again, of the acidic proton, right? Or the stability of the conjugate base after the loss of my proton. Okay, so as we increase the bond polarity, increase my bond polarity, yep, that's going to get confusing. As we increase my bond polarity, we increase the acidity. Okay. As we decrease bond strength, we increase acidity. Right? And as we increase the stability of my conjugate base, we increase the acidity. All right? And so if you think about what that means, right, if I increase the bond polarity, it's easier to lose that proton, right? If the proton is basically has very little access to the electrons, to which keeps it stuck, right, it's more readily lost, right? If I decrease my bond strength, which kind of goes hand in hand with bond polarity, right, meaning that bond of the hydrogen to whatever it's stuck to is weaker, right, it's easier to lose, right? And if I increase the stability of my conjugate base, which sort of means I put more and more electronegative species on my conjugate base, right? If I increase the stability of my conjugate base, then it's easier for my proton to leave also, right? So all those things increase my acidity. All right, so moving on, let's look at, this is one of the figures from your book, and it's a small section of our periodic table, right? So here it says increasing acid strength, which is kind of confusing if we think about these acting as bases, right? And these are weak acids, and neither acidic or basic. Terminology would be better if we just said more acidic or less acidic, right? As opposed to strong and weak bases and strong and weak acids, right? If we're trying to compare a series, right? So if we think about going across a period, right? What do we know about, so obviously we are excluding the hydrogens, right? We're just talking about the elements. So as I go from carbon to nitrogen to oxygen to fluorine across a period, what do I know? Some of my periodic trends, what do I know? Especially in light of the fact that we're talking about being bonded to something else. Right, electronegativity. As I go across the period, I increase my electronegativity, right? As I increase my electronegativity, what also happens as I go across here? Right, increasing bond polarity. Right, meaning that this bond gets more and more polar as we go across the period, yes? So that here, this is much more polar a bond than this OH bond, right? And again, we are talking about that bond, right? We're talking about that bond, right? This bond, right? This bond, right? This bond, the bond to the acidic proton, right? As that bond gets more polar, then that hydrogen shares less of that electron density, meaning the electron density is pulled more over, which means that that hydrogen is more readily lost, which is why compounds are more acidic as we go across the period. Yes? Likewise here, more acidic as we go across the period for the same reason. Yes? All right, let's talk about going down the period. Let's talk about going down the group. Okay. This color should work. As you go down a group, right, think about fluorine versus chlorine versus bromine. What do we think about? What do we know? Group trends. Right? We know that it gets larger, right? We know that, what can we say? Radius increases. All right, as we go down the group, we know that radius increases. As radius increases, thinking back to Coulomb's law, right? As the radius increases by default, right, the attraction between these two diminishes a little bit, yes? As the radius increases, the attraction between these two decreases to some extent, meaning as we go down, there is a decreased bond strength, okay? Decreased bond strength. As we decrease that bond strength, radius increases, we could also say increase our bond length, right? Because the radius increases, we increase our bond length. Between these two things in Coulomb's law, that decreases our bond strength. As our bond strength decreases, we see that our acidity increases, yes? Acidity increases, acidity increases, acidity, it doesn't really matter here. Yes? Does that make sense? Right? So we could say that it is more acidic as we go across a period and my electronegativity increases, therefore my bond polarity increases, meaning that the hydrogen is less attracted or is less strongly attached to my other species and is more readily lost. As we go down a group, the radius of my other species increases, my bond length increases, therefore my bond strength decreases, therefore my proton is more readily lost, and the acidity increases. Okay, so that's mostly for, right, and that applies to this specific kind of analysis where we're talking about some element stuck to hydrogen, right, and that's all this analysis is, right. Here, this is analyzing a set of oxyacids, very specifically, right, an element stuck to an oxygen which is stuck to my hydrogen. Yes, so hypochlorous, hypobromous, and hypoiodus. Yes, does that make sense? And they write it here as YOH. I think that's a little bit misleading, right? It would be better if we said YOH with a bond there, so you don't try to think this is a hydroxide group, which could be confusing, right? So maybe write it this way, okay? Here, as Y gets more electronegative, we see that the more electronegative Y is, right, the more acidic it is, right? And this also goes to bond polarity, right? As this species gets more and more electronegative, right, it pulls electron density away from my hydrogen, yes? Pulls electron density away from my hydrogen, which means that this partial positive sort of becomes more partially positive, which means that it is more attracted to the lone pairs of my water, which means that proton is more readily taken away, right? Which means that we are more likely to form these two species, right? Which also what happens there, right? The more electronegative that Y species is, the more stable this resulting conjugate base is, okay? The more electronegative this is, the more stable this resulting conjugate base is, all right? So that's the analysis we would use for this kind of an oxyacid, right? Where if we have a set, the more electronegative that one other species is, right? Then we would say the more polar this bond is, the more partial positive that is, the easier it is to take that hydrogen, or the more attracted that hydrogen is to the lone pairs of an adjacent water molecule, and the more stable our resulting conjugate base, therefore the more acidic our compound is. Now, this is a different analysis. Yes, do you see that this is not the same kind of analysis that this is, right? Here we're analyzing a set of the same type of oxyacid, right? Here, this is a set of oxyacids from the same basic thing, right? This is all based on like chlorate and then the chlorate derivatives. Yeah, do you see that? Okay. So when we're analyzing this set, it's the same idea, right? So the more polar we make this bond, the stronger the acid, right? And that has to do with here, right? So we talked about here that the more electronegative this was, the more polar this bond is, right? So if we think about that, what that means, so if we don't change the species, but we attach something electronegative to it, right, all the more it pulls electron density away from that hydrogen. Attach another electronegative species, right, more electron density is pulled away, and again, even more electron density is pulled away. So here it's the same idea, where this bond gets more and more polar, which means that this gets a stronger and stronger partial positive, which means it's more attracted to the lone pairs from a neighboring water and more easily removed, right? And the more electronegative groups here, the more stable this conjugate base is. Therefore, we get a stronger acid. Yes? All right. Thank you for listening. Be good, and I will see you soon for Chapter 17. All right. Bye.